So we're going to go over in this video heat capacity and how we can utilize heat capacity to calculate the changes of energy or enthalpy for a given temperature change. So a lot of the times we're going to have to deal with formulas for the heat capacity. These are the formulas from the book. These are in Appendix D of the book, and it has a lot of tabulated data there. And really these are heat capacity, this is heat capacity data for gases. And the formula for our heat capacity equation is of this form right here. Cp divided by R is equal to A plus Bt plus Ct squared plus dt cubed plus Et to the fourth. And then you have all this data listed there in this table, and I've only listed one example. This is for methane, but we have A, B, C, D, E values here. First thing I want to point out here is that these values right here in these tables are not what they are written down here. So if you just take this value A and plug it in here, well, A you'll be okay, but if you take B and plug it into here, you'll be wrong, or C, or D, or E. So these values here are actually have been multiplied by this number right here, this 10 to the whatever power is given, 10 to the third, 10 to the fifth, 10 to the eighth, 10 to the 11th, etc. So in actuality, B in this case, B is equal to negative 8.975 times 10 to the negative 3. And then C is equal to 3.631 times 10 to the negative 5. And D is negative 3.407 times 10 to the negative 8, etc., etc. So you just have to realize that these numbers are actually have this 10 to the minus 3, 10 to the minus 5, or 10 to the minus 8th or 11th tacked onto them. And again, that's because this is B multiplied by 10 to the third. So to get B itself, we need to multiply by the inverse of it, which gives you this here. The other thing that we have to realize with this equation is it only works as temperature if it's in Kelvin. So if we have the temperature in something other than Kelvin, then we need to make sure we definitely convert to Kelvin. Otherwise, if we use these formulas, we will have problems and we'll make mistakes and we'll get the wrong answer. The other part I want to point out is that this equation up here is Cp divided by R. So it's not Cp itself, it's Cp divided by R. So the common value that we use for R in this equation, listed right here, R is equal to 8.314 joules per mole Kelvin. So if we want to get Cp itself, we have to take this whole equation and multiply it by R here. So how do we go about actually using this equation? So in this case, I simply took Cp and divided by R and multiply it by R, and so I get the actual equation for Cp itself, this equation right here. Now the equation that we're going to use relates to the change in enthalpy. Remember that when we're dealing with Cp, we're dealing with changes of enthalpy. And this is the equation listed right here. The change in enthalpy going from one state, state 2, or from state 1 to state 2, is this equation here. It's an integral equation, so we have to do a little bit of integrals. This H2 is simply the enthalpy at temperature 2, and H1 is simply the enthalpy at temperature 1. So we go ahead and apply some integration here. So if I go ahead and write out all the equations, this is what I get. So if I just take delta H is equal to R integral of T2 to T1 of Cp delta T, I just take this equation for Cp, plug it in here, that's what I got right here, and I have to integrate it, and if I did my integral correctly, which I believe I did, this is just AT times AT plus BT squared over 2 plus CT cubed over 3 plus DT fourth over 4 plus ET fifth over 5, and we integrate it between T2 and T1, so we would evaluate this expression at T2, and then we would subtract the same expression using T1 values. And then again, A, B, C, D, and E are all tabulated values from the chart at the back of the book. So we just need to go ahead and plug them in to evaluate it between the limits of T2 and T1 in order to get the change in enthalpy when we're going from one temperature to the other. So let me just close up this by talking about changes of internal energy. So when we're dealing with a system that's a closed system, we'll deal with changes of internal energy, but when we're dealing with flowing system or open systems, we'll deal with changes in enthalpy. The equation for the change in internal energy using heat capacity is the one given right here, where it's again integrated between the limits of T2 and T1 of CV dt. Well, for an ideal gas, and again, ideal gas, let me make sure this is clear. This is the equation that holds. If we're dealing with something besides an ideal gas, this equation may not necessarily hold. So this is the equation for an ideal gas. Cp is equal to Cv plus R. So we can use this information in combination with the Cp values that are given in the back of our book or maybe given from other sources to get Cv. So in this case, Cv is just Cp minus R. So we would have to take this into account, this minus R, or this part right here, when we're doing the integral here if we get our Cp value from a formula or from a table. Let me just mention one other thing, that oftentimes for solids and liquids, Cp is approximately equal to Cv. So in this, oftentimes when we're dealing with liquids or solids, they're basically the same thing, whether we're at constant volume or constant pressure. And we take one or the other and we use that for calculating changes in internal energy based on temperature changes. However, again, for gases, that's not necessarily the case. And for at least for an ideal gas, for a gas that's taken as an ideal gas, this is the relationship. And so now we have a way, again, to remind you of dealing with changes of energy, whether that's internal energy or enthalpy, based on temperature changes using these integral equations for heat capacity.